And we've got a terrific talk tonight from the Young Turks. My goodness, we do have the bright and beautiful to talk to you tonight. And what changes they're going to see in their future careers. So, Hammersmith Connection Tunnel and our two Young Turks. Peter Coppenhole, Morgan Sindall Engineering Solutions. Peter works for Morgan Sindall Engineering Solutions, an engineering consultancy within Morgan Sindall Infrastructure. He's a chartered civil engineer with over 6 years of experience in tunnelling and was one of the first students to obtain the MSc Tunnelling and Underground Space from Warwick University. He previously worked on the construction of the SEL tunnels at the Crossrail C310 contract, and for the last 2 years has worked as the designer's representative on Thames Tideway West. Ed Batty of BAM Nuttall. Ed works for the Major Projects Division of BAM Nuttall. He's a chartered civil engineer with over 7 years of site experience. Ed's career began as a TBM shift engineer on Crossrail contract C300-410. His experience on this TBM was the focus of his Harding Prize paper, which won the competition in 2014. Over the last 7 years, Ed has been exposed to various types of tunnelling, including handworks, SEL primary and secondary lining. Ed is currently working on the Frogmore Connection Tunnel, where he holds the position of tunnel manager. But just before we start, if you could make sure any mobile portable devices are switched to silent so that our two Young Turks get a clean run of it. There are no fire alarms or any other stuff, so if you get a fire alarm, I guess it's a good idea to leave the building. Okay, we've got a few more coming in, and then once we've sat down. There are seats at the front, Woody. You can come down here. Don't be shy. You're not normally. Okay, off you go.
Good evening, ladies and gentlemen. Tonight we're going to talk to you about the Thames Tideway Tunnel, and the focus of our presentation will be on the Hammersmith Connection Tunnel. I'll start off with the problem, and it's a problem I'm sure you're all aware of. Sir Joseph Bazalgette built our sewers in the 1850s, and he designed them for 4 million people. There are now 9 million people flushing and washing in our city, and Bazalgette's sewers are full to the brim. With every downpour, these sewers overflow via a series of CSOs, also known as combined sewer overflows, and they overflow into the River Thames. This happens on average once per week, and the result, 39 million tonnes of raw sewage entering our river every year. So how to solve this second big stink? Well, luckily for all of us in this room, the solution came in the form of a 25-kilometre long segmentally lined tunnel. The tunnel starts at Acton in the west and spans across London through to Hammersmith Pumping Station in the east. As it spans across London, it picks up 34 of the worst offending CSOs. Once operational, instead of this sewage entering the river, it will make its way to the tunnel, where it will be stored and transported to Beckton Treatment Works for safe treatment. Given the scale of the scheme, the tunnel was split up into 3 key contracts, namely West, Central and East. The Western contract, contract C405, was awarded to the BAM Nuttall, Morgan Sindall and Balfour Beatty joint venture in September 2015. It was procured using an NEC Option C single-phase design and construct contract. The joint venture has 3 key designers undertaking their design. They're now shown on the slide. A point of note is that Morgan Sindall Engineering Solutions are responsible for the shaft and tunnel temporary and permanent work design. The scope of C405 West comprises 7 key shafts, most of which have been designed and constructed using SCL linings. 5 of those 7 structures are now complete, and over 15,000 cubes of SCL have been applied in that process. Our main drive is a 6.9 kilometre long single bore of 7.1 metres internal diameter. Our drive starts in Carmouth Road and goes west towards Acton storm tanks. Our main tunnel TBM, Rachel, is about 450 rings in. She's got a long way to go, but she's making good progress. She's constructing our tunnel with a lookup of 1.4 millimetres per metre. So far, she has churned up and spat out over 70,000 tonnes of London clay from beneath the river. The scope of West also involves 4 smaller connection tunnels, and these have been constructed using a range of methods, including mechanised tunnelling, pipe jack and SCL. The focus of our presentation will be on the Hammersmith Pumping Station, and you can see that on the slide now. So, to set the scene of Hammersmith, I'd like to set off with this picture of 5 operatives at work. These 5 highly skilled men have been given the gruelling task of working in the live inlet channel of the Hammersmith Pumping Station. They're working in the close proximity of raw sewage mixed with discarded wet wipes and sanitary products. The works must be undertaken while keeping the pumping station live, as if it goes offline, this may result in the catastrophic flooding of West London. The Enolate Channel is just one key element of this asset of national importance. It channels storms over relief flows into the pumping station, where 8 stormwater pumps pick them up and pump them out into the Thames. The works in the channel are planned in such a way that the men and their tools can be removed quickly in the event of the storm. The channel is 18 metres deep, 5 metres wide, and 25 metres long. When storm relief flows make their way to Hammersmith, they enter the inlet channel of a flow rate of up to 30 cubic metres per second. Now, to put that into context, this great theatre is 18 metres deep, it is 12 metres wide, and it is 8 metres high. It therefore has a volume of 1,700 cubic metres. I'd like you to imagine that the storm flows are entering this room and not the Hammersmith Pumping Station. On entry to the room, it would take just 9 seconds for you all to be swimming in sewage. In 55 seconds later, the room would be full and we'd be in serious trouble. The Hammersmith site was signed over to the B&B joint venture in the summer of 2016, and works have been going on since. The site is surrounded by a number of key residential receptors and sensitive assets, such as Frank Bankfield Park to the north, and the residents of Chancellor's Road and Fulham Reach to the southwest and east. The works at Hammersmith are very typical to other CSOs on the scheme. Their purpose is to transfer the flows from the pumping station into the main tunnel, and that is achieved through an interception chamber, a connection culvert, a drop shaft, and a connection tunnel. The interception chamber is being constructed directly adjacent to the inlet channel, and the works here are progressing well. The team have now excavated over 4,000 tonnes of material and have just started the internal structures. Once complete, the interception chamber will house a series of penstock gates, which will control flows into the new tideway scheme. The connection tunnel, this is 300 metres long and juts out into the centre of the Thames where it meets the main tunnel. The tunnel passes under a number of key assets, including the river wall and 2 blocks of luxury flats with an average value of 1.4 million. I'll now pass you over to Peter, who will take you through the design of the works.
Before you start, did anybody stood at the back? There are seats at the front here. If you could come down maybe, and I see there's somebody actually stood behind the parapet there. There's plenty. Don't be shy. There are plenty of seats at the front.
Okay, before I take you through the design, I will take you through the geology of Hammersmith. From the initial ground investigation that was carried out by Thames Tideway and outlined in the GBR report, you can see there's only a few boreholes that were sampled. B&B undertook further ground investigation to confirm the consistency of the ground and of the GBR. And from this initial ground investigation, it was consistent with what the GBR stated. The geology comprises of made ground, overlying River Thames deposits, the London Clay Formation, and the Lambeth Group. The connection tunnel was situated in the ideal location. It's in the middle of the London Clay Formation. It has a 90-metre cover towards the Lambeth Group, and it has 20 metres clay cover to the crown of the tunnel as it passes out underneath the River Thames. From the ground investigation data, we're able to tell that the piezometric level was recorded at 100 metres above tunnel datum, but for the purpose of design, 105 metres above tunnel datum has been assumed, which is consistent with the existing ground level. Here is the overview of the client reference design. This shows the key requirements for the design development. We have a 35-metre deep shaft with 11 metres internal diameter, a 48-metre long deaeration chamber with a 5.1 metre internal diameter, and a 250-metre long connection tunnel with a 4 metre internal diameter. Both the tunnel and the shaft required the use of a primary and a secondary lining and the use of a waterproof membrane as well, so it could comply with the strict water ingress requirements. There is a B&B MSCS innovation to remove this waterproofing, which required consent from Thames Tideway as well. There's a 3.5 metre internal diameter stainless steel tube in the middle of the shaft. The purpose of this is to transport the sewage down from the top of the shaft to the bottom of the shaft in a harmless manner. Otherwise, if the sewage came down on itself, it would come crashing down to the floor and it would damage the structure. The way this works is by creating a vortex within this tube. So the sewage comes towards the top of the tube and it spins down the shaft all the way down to the bottom in a harmless manner. Now we've undertaken a number of computational fluid dynamic models and real-life scale tests were undertaken just to verify this assumption. And this short video shows how the sewage will travel along the connection culvert and down the shaft as a vortex. The next video that I'm about to show will show another scaled-down model, which is about 1/10 of the size of the actual shaft. And just to note, as the water comes out of the bottom of the vortex, you'll see the amount of air that is generated in this. This is as we go along the connection culvert, down the vortex. So as you'll note from that video, there's a lot of air that's generated at the bottom after the vortex. And it's really important that any of this trapped air is removed from the system so it doesn't cause damage in the future. So this is where the deaeration chamber and the vent pipe come into play. As the sewage moves from the shaft and into the deaeration chamber, there's a flow restrictor wall at the end of the deaeration chamber, which basically holds up the sewage just long enough to allow the air to basically rise to the surface and leave the sewage. It then travels along the top of the deaeration chamber, out the vent pipe, and back up to the surface in a harmless manner. For the design, the works information sets several key requirements. 120 years design life, to be able to accommodate the predicted sewage flows and the surge pressures that would be experienced by both the shaft and the tunnel. To comply with the strict water ingress requirements and the sewage egress requirements. To minimise the requirement for repair, replacement and maintenance of the works as well. And finally, the design construction must stay within the boundaries that are stipulated by the development consent order. And in terms of Hammersmith, this is very tight, which Ed will touch upon later. As already mentioned, the water ingress requirements are very strict. As you can see here, the maximum acceptable water ingress into the completed shafts and the tunnels are 0.1 litres per metre squared per day on average, or 0.2 litres per metre squared per day over any 10-metre section. Part 2 of this clause also states that it's limited to damp patches, which is defined as discoloration of part of the surface of the lining. And this part can be open to interpretation and has caused issues as well. Well, not issues, it's caused points of contention along the way. Part E also states that limitations on seepage apply to both ingress and egress. So we have to ensure that the water doesn't come in and the sewage doesn't escape. And this is verified by observation and measurement within the tunnel. And for outside of the tunnel, it's verified by calculation and monitoring the groundwater quality in the local area. These strict requirements have been outlined by Tideway to ensure that the maintenance and operations costs of the system is minimised across the whole of the Thames Tideway scheme. I will now give you an overview of the design development gated process, which is very similar to the Reba stages. As a design and build contract, the contractor has been heavily involved throughout all of the stages, from gates 1 to 6, and they've helped develop the design through the use of several constructability meetings. A key stage here is gate 3, where we had interdisciplinary reviews. These were with the likes of Mica, hydraulics, architecture and landscape, operations and maintenance, and many more. And it's key that this was undertaken prior to progressing on to detailed design. Also at Gate 3, this is the first instance that the Thames Tideway Design Engineering team and the Design Authority were able to comment and approve the design and the initial design concept. BIM has been used throughout the project to help coordinate the designs and provide a single point of reference for information. This has been available for all parties involved in the contract. The Hammersmith Design started in September 2015, along with the start of the contract. The primary lining for just the shaft finished in December 2017, and for the tunnel, the primary lining and the secondary lining finished in April 2018, so not very long ago. The shaft secondary lining is close to being finished, and the internal structures, the vortex and the cover slab are still ongoing. Here's an overview of the Gate 5 design. Each of the elements that have been specified here are to comply with the durability requirements in terms of the mixed design and the design crack widths. This is in order to make sure that it meets these tight water ingress requirements. The first stage you can see here is the secant pile wall, which is highlighted in red. And this enables the initial shaft excavation in the River Thames deposits while cutting off the water ingress from the water-bearing gravels. The secant pile wall is only temporary works. However, it will remain in place for the length, the duration of the structure itself. The shaft primary lining was created with steel fibre reinforced SCL with 1.2 metre advances as it progressed. The shaft primary lining and the SCL allowed flexibility, so therefore in order to minimise the thicknesses and also the amount of material consumed. And as we progress down to the bottom of the shaft, it also has an elliptical shape which incorporates the tunnel opening portal. There's a thickening section here which uses traditional bar reinforcement, which is also to be sprayed in. At the bottom of the shaft is the base slab. This is a 2.2 metre thick base slab, which is designed as a flat-topped structural dome. And this resists the long-term pressures of uplift from the geostatic and water pressures. The shaft secondary lining has hybrid reinforcement, so it utilises high-performance steel fibres and traditional bar reinforcement. It's up to 800 millimetres thick in places. The traditional bar reinforcement helps to tie in the accommodating structures inside of the shaft. So this ties in any of the internal structures and the vortex tube itself. The tunnel primary lining is also installed in a similar manner to the shaft. It's steel fibre reinforced and is installed in 1 metre sections and is 325 millimetres thick. The shaft's secondary lining is 250 millimetres thick, and the design follows the smart shell technique, which removes the requirement for traditional bar reinforcement and uses high-performance steel fibres, in this case which are Drumex 5D fibres, to replace any of that reinforcement. And this technique was proven beforehand on the Lee Tunnel project by full-scale tests and has been verified since. There have been some lessons learned from the Lee Tunnel project, such as we've reduced the length of the bay of the shutter from 30 metres down to 6 metres, and we're also ensuring the shutter's pulled with full hydrostatic pressure as well. There are two principal design load cases, which are calculated from the dominant loading conditions that are experienced. Design case 1 is the highest external pressures that the shaft and the tunnels will experience. As you can see, it will have geostatic pressures from the ground, and it will also have the highest groundwater pressure. So in this circumstance, at 105 metres above the tunnel datum. This will oppose the shaft and the tunnel at its weakest state, and in the worst load condition, which is when the shaft and the tunnel are empty. This will incorporate the maximum bending moments and stresses that are anticipated to develop in the structure. So this therefore overall governs the design of the shaft and the tunnels. For design case 1 as well, an additional surcharge has been placed on the surface, and this just represents any future developments that will be undertaken. Design case 2 is the highest internal pressures that will be experienced. So the ground loading stays the same, the groundwater pressure will be reduced to its lowest known level, and the shaft and the tunnel itself will be full. And this represents a surge event. To be able to understand how the primary and secondary lines work, we need to understand how they're installed. The primary lining first is installed sequentially, as mentioned, 1.2 metre advances or 1 metre advances in the tunnel. And this takes all the initial groundwater loading and all the ground pressure as well. The secondary lining is then installed in a stress-free environment. However, over time, additional external pressures are experienced by the shaft and by the tunnel. This is resulting from clay consolidation, changes in groundwater, seepage, the surge events. And it causes the primary lining to deform, which then activates the secondary lining, which results in the two linings working together in a combined manner. When in operation, the primary lining will always remain in compression, and the secondary lining will go into tension in the surge event. This shows a typical section of the completed lining. We have a 75 mm initial steel fibre reinforced SCL. This is for the immediate ground support of the excavation, but it also offers an additional protection measure. So it protects the structure from sulfate attack from the groundwater, and hence is not considered as part of the structural thickness of the structure itself. The primary lining, also steel fibre reinforced, and will be the same mix as the initial layer itself, is our sole purpose of watertight measure. It uses steel fibres to control the cracking in the temporary condition. So this is during the installation when bending is expected. And as mentioned, it provides the only water tightness that we have, as there's no traditional membrane in between the primary and the secondary linings. The secondary lining itself is cast up against the primary lining. As mentioned before, it's reinforced with Duramex 5D fibres, and some areas have rebar as well. And to be able to control the crack widths and limit the crack widths down to less than 0.2 millimeters, this is why they're in place with the reinforcement. And this ensures the durability and promotes self-healing of the concrete as well. In order to have a watertight spray concrete lining, the design has stipulated a bespoke SCL mix, which has a low water to cement ratio, and a low permeability. A crystallization agent has also been put into the mix to help enhance the mix as well. There's been a key focus on joints. The joints have been detailed such that they're 45 degrees. They need to be clean, free from contamination and steel fibers exposed, as you'd expect from a good quality SCL joint. However, to help with any poor workmanship or any bad joints that may be experienced, we've also offered a more belts and braces approach. And the sequence itself has been staggered. So if you imagine a 400mm thick lining, if you had one place of water ingress that comes through that lining, it only has to travel 400 millimeters. The staggered approach allows that to travel through 2 different areas and extends the water path up to about 1 meter, which greatly reduces the chance of water ingress. We've also used secondary measures in high-risk areas such as around the base slab and around any junctions as well. And this includes re-injectable tubes and water bars. Here you can see the key requirements that, as the designer at MSCS, we've outlined for the watertight SCL mix. The steel fibers require a minimum tensile strength of 1500 MPa. The mass spray concrete requires a low permeability coefficient of 1 × 10 to the minus 12. Now, to put that into context, normal spray concrete has a permeability coefficient of around about 1 × 10 to the minus 10, and up to around about 1 × 10 to the minus 12 as well. So we need to make sure that we're better than this. And not just across the mass spray concrete, but also at the joints as well within the spray concrete. The key addition here is the crystallization agent, and in this case, we've used Zypex with a recommended dose of 5 kilograms per meter cubed. And the way this crystallization agent works is that it's infused with the mix itself, so it actually becomes part of the mix, and it reacts with any moisture that travels through the concrete. And by reacting with the moisture and the byproducts of cement hydration, it's able to form insoluble crystals within the capillaries of the concrete, which helps provide further assurance of a watertight concrete. The final mix that was used by B&B was developed in conjunction with CPI and BASF, and a lot of testing was undertaken. We now have a look at the effect of adding this crystallization agent had on the mix itself, and you'll see how it affected the early age strength development and the plastic properties. This graph here shows the early age strength development that was required. We have the J++ curve, which is a more onerous curve than the standard J2 curve that's used in spray concrete, as it requires a higher and earlier strength gain. And this was the curve that was stipulated for use in the design. As you can see, with the addition of Zypex on our control sample, with a 7% accelerator, it was not able to meet this in the early hours. On the workability as well, when we added the Zypex, it reduced the retention time down from 4 hours to 2 hours, or under 2 hours in this circumstance. So it's not very reliable. Through working with CPI and BASF, it was identified that the Zypex was interfering with the superplasticizer, was delaying the strength gain of the concrete. Once this was realized, the superplasticizer was changed, and the accelerator was changed from SA160 to SA194. As you can see, with the new super plasticizer and the accelerator, we're easily able to meet and exceed the J++ requirements. And you'll note this is actually with a lower accelerator as well, with only 6.5%. The other testing of 5.5% also exceeded this, and that's generally where we look to spray between 5.5 and 6.5%. The workability as well was improved to a minimum of 2 hours, and this was deemed adequate for the site team. Here are a series of photos from the trials taken in July 2017. A numerous amount of tests were undertaken with about 40 flexural beams and 25 panels. The concrete proved easy to spray with low levels of rebound and good compaction. This was regardless of location, so such as the invert, the shoulders, the mix proved to be very good. And as you can see from our cores and our flexural beams as well, we managed to obtain a very good mix. There is a particular focus on the joints. So here on the left-hand side, we've set up a panel. The way we'd go about this is we'd spray the first-hand side, and we'd try and we would form the joint during the spraying process. After sprayed, we'd come along, we'd clean and tidy up the joint with a high-pressure jet wash, similar to what we'd actually do in the works. We'd leave the sample for 24 hours, after which we'd return and then spray the rest of the panel. Once the panel was complete and cured for 28 days, we'd come back and we'd core directly through the middle of the joint, so we were able to test this joint for compressive strength and, more importantly, permeability. 2 water penetration tests were undertaken on the mix. The first one was a European standard test, which is specified in the works information. This tested the sample for 72 hours under 5 bar. The second test was a Morgan Sindall developed test. It's a far more onerous test, as it's tested for 96 hours under 10 bar of water pressure. And it doesn't just measure the water penetration, but it also measures the amount of water left within the sample as well. And from this, we're able to ascertain the water permeability coefficient. And as you can see on the screen, this is a general setup of testing equipment. And what we're trying to achieve on the right-hand side is just very low penetration. After 6 weeks of trials, B&B develops their final mix. They selected Dramax 4D fibers to be able to meet the minimum tensile strength. The permeability coefficient was a minimum of 7 times 10 to the minus 14 across both the mass spray concrete and the jointed samples, which is much lower than our requirement. And the addition of Zypex was still included as well. The addition of Zypex, eventually we managed to be able to satisfy the Enolate strength, but it has hindered the workability retention of the mix. It's also important to note at this point as well that because of the addition of Zypex and the change of the admixtures, we experienced a higher cost of the SAL mix of around about £60 per metres cubed. I'll now pass you back to Ed.
For those of you stood at the back, there are seats at the front, so we'll just take a couple of minutes while Ed is getting ready for you to come down. There's plenty of seats at the front.
Okay, so the pit top setup works for the shaft sinking and tunnelling works commenced in the summer of 2017, and this in itself was quite a puzzle to solve. Given the proximity of these nearby receptors, the focus of this setup was to minimise the noise and nuisance associated with the works. Initial ideas pointed towards the use of an acoustic shed, which would be placed over the shaft, craneage and batching plant. But given the tight constraints of the DCO, we were not possible to do that. As you can see from the image, the site boundary we were given was a mere 2 metres away from the exodus of the shaft. So this is the compromise site setup we came to. I'll start with concrete batching. We initially considered the use of a traditional plant. Given the tight available working space, this was not possible. It was also not seen as wise to have aggregate bins that were loaded day to day because of the noise associated with that. Due to the issues with the mix and the flow retention reduction, ready mix would also not be feasible. Additionally, the code of construction practice only allowed deliveries between 8 and 6, and we wanted to tunnel on a 24-hour basis. So the selected solution was provided by CPA Euromix, and this was a pre-blended silo system. This system works by mixing all the dry constituents off-site and kiln drying them, and then they're delivered to site in a tanker and blown into the silo. All that's left to do on site is dose the mixture with water, and that's done with a screw at the bottom of each silo. We went for 4 silos with a total capacity of 350 tonnes, and this gave us about a week's supply. The next point of interest is the electric drive crane, and this cost an absolute fortune. But as you can imagine, it's quite neat use of the space. The southern beam spans 13 metres over the shaft. This was also a lot quieter than a diesel crawler crane. The runway for the crane, there was a real focus on the design of that. So any metal to metal or metal to concrete components had rubber pads on them to minimise the vibration. The runway was equipped with a number of flat jacks, to enable the team to take out any settlement as the shaft sinking and tunnelling works progressed. The last point worth noting is the Muck Pin Design we went for. And following a number of quite high-profile near misses on Crossrail with precast L blocks, we decided to go for a quite robust, again expensive, king post Muck Pin alternative. We saw this as best practice and a way of reducing the risk. As you will have gathered from Peter, the design required a high focus on quality SCL, and this was very much in the back of our mind when planning the works. And we saw these 3 building blocks as key ways of driving that high quality. We needed to attract a highly skilled and experienced workforce. We needed to drive ownership between the gangs. As you'll all be aware, if there's many gangs, it's always the gang's fault who's not on shift. We also wanted good levels of workforce morale. We saw the best way to solve all 3 blocks was through the proper selection of a shift pattern, actually thinking about that. So here are the shift patterns we went with. Drop shaft shift pattern, very straightforward. 10-hour shift, Monday to Friday, no weekend working. The tunnel shift pattern, we went for a 5-2, 4-3 shift pattern with an 11-hour shift. Again, no weekend working. The 11-hour shift didn't comply with one of the key red lines of the works information that had been set out, and that was a 10-hour shift limit on tunnel workers. But through fatigue analysis, we could show that actually this had a lower fatigue score than a lot of the traditional shift patterns, 7-2, 7-2, 7-3, where you work in 8, 9, and 10 hours. So dispensation was received. However, there was a number of conditions attached. We had to provide regular questionnaires to the workforce to gauge morale and fatigue, and also provide fatigue awareness training for all key members of the workforce. Shaft sinking took place early 2018, and we were the first team on Tideway to start SCL. Peter described the shaft earlier. We split it down into 29 advances of 1.2 metres. The lining thickness changes as we go down the shaft, and we could only start the staggered joint detail that Peter talked about from advance 4 onwards. Excavation of the shaft, that always followed the same process. Bulk mucking of the centre to advanced formation using an 8-ton excavator, and then trimming the berm, a 1.8 metre deep berm, back to profile. The next step, this was the key step in the whole construction process, joint preparation. So there's 2 stages to this. Stage 1, inspect the joint and identify any poor SCL or overspray. Then if there was any poor SCL or overspray, remove this with an excavator-mounted rock wheel. The second stage, we then jet washed the whole joint using a high-pressure jet washer. Quite a lethal thing, and this was robot-mounted. So here's what a good joint looked like. On the left, you can see the 600mm stagger between the SCL layers. And on the right, 45-degree joint with fibres exposed, free of poor material. A point worth noting is one of the key hold points in our ITP was the inspection of these joints. And every joint required sign-off by an engineer with a minimum of 5 years SCL experience. Application of the SCL, dead straightforward, 2 layers. We did this continuously if possible to provide a good bond between the layers. And then finally, the leading edge was green cut before starting the next excavation. Throughout all our SCL works, best practice from Crossrail was adopted. This included air-fed RPE and Bluetooth communication for any operative in any SCL restricted area. In terms of testing, we went above and beyond the minimum works information requirements. We needed good quality SCL day in, day out, and that was absolutely critical for the design. To do that, we set out a daily workmanship panel, and this was done at a frequency of 1 panel per nozzleman per day. So if 2 nozzlemen sprayed a shaft advance, we'd spray 2 panels. These panels would be cored, inspected for workmanship, compaction, voidage, and compressive strength. It might seem over the top, but it meant we could identify any issues with the workers or the equipment within 24 to 48 hours. It's really critical. So there's a picture of the completed shaft. In total, it took 15 weeks to complete. We had an average advance rate of 2.4 advances per week. Over 1,000 metres cubed of SCL was sprayed in the process. In terms of settlement, we achieved 19mm, or 19.1mm, and our prediction were 19mm, so bang on target with that. Moving on to the tunnel. The tunnel was split up into 1 metre advances. There was 295 in total. The face was excavated using an ICT 120 heading excavator, and the 15 tonnes of spoil from each round was transported to pit bottom using a series of track dumpers. Once at pit bottom, it was lifted to the surface using the Goliath crane. Like with all our tunnel headings on Tideway West, the laser shell method was adopted. That makes use of a remote profiling system called the tunnel beamer and also an inclined face. As you can see on this exclusion zone management plan, our face was inclined to 20 degrees to the vertical. This significantly reduces the risk of injury associated with SCL fallout. This is adopted throughout Tideway West, and I'm proud to say to this day, we have not asked one engineer or operative to work below freshly sprayed concrete. I think that's a really strong point. In-tunnel ground investigation was undertaken using probe drilling at 12-metre intervals with probe 16 metres ahead. And what we found was consistent with this site investigation. On this image, you can see a clear interface between London Clay Units B and A3II, and that was denoted with a band of claystone in the face. The tunnel detail was slightly different to the shaft, given the constraints of its diameter and the lining thickness. So we were able to adopt a large stagger, but we still had a stagger. We had a 100mm initial layer, and then a minimum of 100mm stagger between that and the primary layer. Like the shaft, we were looking for the same joint quality, so 45-degree joint, fibres exposed, poor material removed. The preparation of this joint took place in a similar manner. Any poor material rock wheeled off and then high-pressure jet washed. This was a bit more challenging than the shaft, so we found that the rock wheel often damages that leading edge, that initial, and it'd be broken away. Shotcrete for the tunnel was batched on the site surface and pumped 350 metres to the face. We started by applying the initial from the invert and working to the crown, blowing that out, and then applying the primary layer again, invert to crown, all in one operation. There was a real focus on management of the dust during the invert section. This is an example of a man on a blowpipe, blowing away rebound from that critical trailing edge. However, this is a challenge. You're very much reliant on the skill of that man to ensure there's no contamination of that joint. Challenges of joint preparation aside, the tunnel advanced at a good rate. It took us 22 weeks to complete, and we achieved an average production rate of 14.1 metres per week. This rate actually meets the requirement we set out in the tender. That was with a 7-day week working shift pattern. So we'd reduced the number of gangs and hours, and we still met the target. In terms of settlement on the tunnel, again, we were broadly in line with the predictions. We had a maximum settlement of 10 millimetres along the centre line. Okay, so the interesting bit. Post-construction of the SL linings, we undertook an ingress check. So we looked at both of the clauses, 0.1 litres per metre squared a day, and the second clause, is there any damp patches with visible movement of water? So I'll start with the shaft. The surface area of the shaft, just over 1,000 square metres. The allowable ingress per 24 hours was at 106 litres, so that's what the works information would allow. Our actual ingress in 24 hours, 0. So the second point, number of visible joints with damp patches with visible movement of water, 0. So following the completion of the shaft primary lining, completely compliant. There was some ingress into the shaft though. There were 2 damp patches. I'll talk you through them now. This is where we missed some core hole repairs on the way down the shaft. So we didn't count that in the analysis. They will be repaired later. But that does provide evidence that water is loading the shaft and it is watertight. Okay, so moving on to the tunnel. Works information allowed 434 litres of ingress per 24 hours. We did our measurements. We had 9 litres in the whole 300 metres of the tunnel. However, we came a bit unstuck on the second clause. We did have a number of damp spots. We had 79 damp spots on the leading edge of the advances. We're not talking about running water, we're talking about damp spots with a visible sheen. We found the second clause very hard to interpret, especially with the client. The conclusion of that was we injected all those damp spots. So here's an example of the typical locations of the damp spots we observed. And as I said earlier, it's extremely challenging to spray a tunnel invert joint without getting dust trapped in it, and this is the evidence. Injection of those damp spots was undertaken in accordance with BSEM 1504, and we used a Type S swelling resin. And there you have it after the injection. We undertook another inspection following doing the resin injections, and the tunnel was signed off as watertight. Okay, so moving on to the secondary lining construction. This is one of the many elements of works at Hammersmith that was a project first, and this was seen as very much being a test bed for Tideway West and the whole of Tideway. The design required a full round shutter, and we went to Kern Tunnel Technic in Slovenia to deliver as a bespoke shutter just for these works. This shutter takes on board a lot of key learning from Lee Tunnel. As Peter said, the first one was the shutter length. At Lee, we were trying to pour concrete into a 30-metre long shutter. Here we've got a 6-metre long shutter. The maximum shutter length we will adopt on Tideway West is actually 10 metres, so 1/3 of Lee Tunnel. The second key learning was design the shutter for a full hydrostatic head. That means we can fill it as quickly as we like. The length and that feature together means you can fill the shutter quick. That significantly reduces the risk of cold joint or voids or poor flow of concrete. The shutter also incorporated a number of key innovations. The first one was the Plc Automation, and this is the first tunnel shutter to have an integrated PLC. So key components of the shutter were fully controlled by that logic computer. That enabled some key data collection and also some new functionality. So we could operate the shutter in semi-automatic and automatic mode. That gave us an extra safety net because it meant we couldn't damage the machine. I'll give you an example. When running this in semi-automatic mode, we could not drive the shutter forwards with the spud bars retracted. We could not collapse the skin with the legs retracted. The final innovation was the use of automatic spud bars. And again, they might look like normal spud bars, but it takes away any manual movements to lock and set these into position. The key aim of the spud bars was for quick setting and also for data collection. Prior to undertaking the works, the site team did some pretty comprehensive pre-trials on the mix development. We started off with 3 ready mix suppliers and whittled that down to 1. That mix was then optimised for filling and vibration. We wanted a good finish in the invert. That was one of the key issues at Lee Tunnel. To do that, we had a bespoke testing station, again provided by Kern, and this made use of some of the forms from the Lee Tunnel shutter. As you can see, the testing station was equipped with a number of key features like the tunnel shutter. It had the same vibrators, it had the same injection ports, it had the same ceramic coating on the forms. The frame of the testing station enabled us to simulate not just the invert, which was done on Lee Tunnel, but also the knee and axis positions. 10 trial panels were undertaken, and with each panel we tried different consistencies, different filling methods, so submerged filling or top-down filling, and different vibration settings, so frequency and pattern and duration. On the left, you can see the testing stations in use, and the trials involved is simulating the tunnel works. So we batched the concrete, delivered it to site, and then pumped it 300 metres to the forms, injected the forms, and vibrated them as planned. On the right, you can see a form that's been struck. Once we'd done this, we'd inspect the surface for blowhole coverage, depth, or any other defects, and also take cores to validate compaction and fibre distribution. As you can see, there's some blowholes present, and that's pretty common when you've got a full round shutter. You've always got a top shutter effect, and what you see there is actually pretty good. The panels enable us to outline what good looked like, and this resulted in a number of trigger points being set for the works. So we had triggers on blowhole coverage, depth, and diameter. The delivery of the shutter took place in March this year, and we assembled 90% of it on the site surface. 500-ton crane came in for the lift, and it was quite a tight one. There was just 250 millimetres clearance between the ventilation structure and the formwork. As the site AP for that lift, I was very relieved after it had dropped past that point. The shutter was lowered to pit bottom, and then the front and rear portals was attached. And then we tested all the spud bars, all the automation, before driving it 300 metres to the end of the tunnel. So that's the shutter in situ. The lining works were undertaken with a day shift and back shift pattern. We actually had a split shift where they overlapped, and we were working 7 till 10 p.m. When planning the works, there was a real focus on how we'd communicate between the pit bottom pump man and the lead liner. Obviously, we did this with radios, but we supplemented that with a radio remote. So the miners at the shutter could stop the pump at any point. That was particularly useful when closing the pore, as it eliminated the risk of overfilling. The spud bars proved to be a success. They were easy to set and quick. The PLC enabled us to program a predetermined preload pressure. So the spud bars would be extended, they'd load the lining to a preload, and then we'd know they were firm in place. Also during pouring, the sensors in the spud bars enabled us to monitor the pressures. This was a useful tool as it enabled us to see if there was any differential filling within the shutter. Finally, we used a timber stop end and quite a robust one, C24 timbers of 150mm thickness, but this was required to hold back the hydrostatic pressures, particularly in the invert of the formwork. All the distribution system was done in steel, and we started off by using 10 of the 16 available injection ports. After a few pours, we identified that the concrete was performing well, it was self-levelling, and we reduced this to 4 pours. The final filling sequence was to pump submerge from the invert up to axis level, and then close the pour with the 2 shoulders. The 35 cubic metres of concrete required for each pour took approximately 2 hours to get it behind the shutter. So here are a few pictures of the finished job. After a sort of slow learning curve, 2 to 3 weeks of a pour every other day, we were hitting our output and we achieved 1 pour for 24 hours all the way through the tunnel. We didn't miss 1 pour. As you can see, the finish is pretty exceptional, and the invert section, that exceeded expectations. You'll see from these pictures that the tunnel's completely dry. There's no ingress at all. So in terms of water tightness requirements, we've absolutely nailed it here. Okay, I'll hand you back to Peter. He will conclude our presentation.
We believe the works at Hammersmith have shown the potential of a watertight primary lining. And we've done a small comparison here against traditional waterproof membranes as well. Each waterproof system has its own merits, and we're not stating that one waterproof system is better than the other. This is just another option to consider for future projects. The comparison does not take into account any of the costs or the trialling times that were undertaken before the work started. As you can see from what's on the screen, there is a potential saving. The number of activities have been reduced. The number of resources required and the different interfaces have also been reduced. Not to mention all the associated paperwork that goes with these, and all the time that you require for approvals as well. In particular for Hammersmith, what was realised in terms of savings was a programme saving, mainly. There was a small cost saving as well associated with these works. And with future developments, there's a very strong possibility that this cost saving could be increased further, with the cost of the mix being reduced and with the length of trialling as well also being further reduced as well. Especially now as the precedent has been set, there's potential that watertight spray concrete lining can be used in future. The removal of the waterproof membrane was a joint B&B MSCS innovation. It was implemented in the early stages of design development. This utilised a bespoke spray concrete lining mix with Zypex, which was to offer us a low permeability concrete across both the mass body of the concrete and the joints. This allowed the primary line to be watertight and to work together with the secondary lining in a combined manner. The philosophy was adopted in the early stages to help simplify construction, to reduce the cost of construction, despite the extra cost of the mix itself, reduce the number of construction stages, save time in terms of programme, offer the flexibility that a primary lining profile can give you in terms of the SCL, reduce the amount of materials used, in particular traditional reinforcement, to meet the durability requirements and to work with the limited amount of space that was on the site itself. The shift pattern adopted by Hammersmith proved to be a big success, working weekdays only. It helped minimise fatigue. It matched the production rates of the tendered 24/7 pattern. It ensured that we had a happy workforce and retained the workforce throughout the whole of the construction of the primary lining and the secondary lining. And overall, it drove good quality as well throughout the works. The final finish of the tunnel exceeded expectations, and this was achieved by the concrete testing carried out prior to the construction and making minor adjustments along the way. All the key learning and the innovations that we've learned at Hammersmith will be taken forward into the main tunnel on Thames Tideway West. As you've seen, the primary lining of the shaft was completed with 100% water tightness without any additional works required. Due to more difficult and naturally dusty environment of the tunnel itself, some leak injection was required to help bring it back within specification. But overall, the watertight SCL, the high quality workmanship that we've achieved, has ultimately led to a dry tunnel at Hammersmith. Thank you.
What a fantastic job and a fantastic presentation. Thank you. I know there are a lot of SCL disciples in the room, so I'm expecting a lot of questions tonight. So if there's somebody sat on the floor up there, do you want to come down in the front? Because you'll be sat on the floor for another half an hour, I think. No? Okay. Right. Can we have a first question, please? Here we go. Benoit.
Hello, Benoit Jones in Bioengineering. Fantastic presentation, thanks guys. It's probably best prepared presentation and presented presentation I've seen here for a long time. So well done. Just wanted to ask, why did the tunnel and shaft need to be so dry?
Yeah, well, this was set out with Tideway, because if you could imagine, if they'd had adopted the BTS specification for a sewer tunnel, they would have been allowed a lot more water in there. But if you imagine all the tunnels on Tideway and all that ingress times 120 years, that's a lot of extra pumping that you need to do at Abbey Mills Pumping Station. So it's purely driven by cost. It's nothing to do with watertightness.
Yeah, just to reduce the cost of maintenance of the whole scheme itself.
Front here. Can you wait for the...
Alex Lee, BMI Tunneling. So the Zypex SCL mix, did you test that against water pressure as well?
Yeah, we did water penetration testing, which I touched upon earlier. So we undertook trials we undertook initial trials way before we wanted to do within the works. So we demonstrated this as an initial case study first. And as I mentioned, we used 2 different water penetration tests to demonstrate the effectiveness of this. And then we further reinforced this by more testing that B&B undertook later on as well.
But that was just a submersion test or something like that. So it didn't, you didn't have a...
Well, the way the test works is the sample itself is basically sealed on all sides, and then we drive a water pressure up uniformly across the bottom of the sample through both mass body concrete and jointed concrete, and then we keep this pressure there for 96 hours.
And what water pressure did you get to for the water?
Well, it was consistent at 10 bar water pressure throughout. And then, as I mentioned before, from this we were able to determine the permeability coefficient because we could measure the depth of penetration and the amount of water retained in the samples.
In the middle here. Good. Just next to Willie. Yep, here we go.
Hi, John from Bailey Consulting, and it's not just a comment. And as a designer, I just have some comments on your innovations. And because your lining philosophy also using concrete-to-concrete direct contact to get rid of the waterproof membrane, basically due to your full strain of the concrete contact, you will have very high early age thermal strain, and also due to the long-term consolidation, your tunnel will deform. So basically, at your crown, secondary lining crown, you will generate pure tension, and that will lead to like through cracks. These things we have seen in Crossrail for a few occasions, and some London ground upgrades, and probably have seen that as well. So for me, I mean, your secondary lining, once you crunk or crack, you become dead weight concrete and does not perform any functionality. And the more problem that because you're in London clay, with the time develops, your lining deformation will be bigger and bigger. Even you'll feel your cracks in the crown. And once it starts operation, the crack will still regenerate. And then you allow the water, the cohesive water, to reach to the interest of the primary lining. For me, it's kind of mistake in the design. So I hope these kind of things probably in the next time could be avoided. Thanks.
No.
That's a statement.
Yeah, thank you. I mean, the primary lining itself is designed to be watertight over the whole duration of 120 years, and it's only expected really to deform in tension like during its installation. So over its lifetime, once it's been installed, all you're going to be getting is compression onto the primary lining. So you shouldn't get any more water ingress than what you already have at the moment. And the secondary lining itself is designed purely for tension. Well, not purely for tension, but it's designed for tension in terms of a surge event.
Another question? Yeah, Charles Allen at the front here. Charles at the front.
Well, first of all, congratulations for creating a dry tunnel in London clay. That's not my question. My question is, you showed a video of the modelling for the hydraulics, and you showed the vortex shaft, the vortex drop shaft. Tremendous amount of aeration at the bottom of that. Yep. That can create a problem called cavitation. What's being done to mitigate against cavitation of the base at the bottom of the shaft?
There's a certain amount.
If it's just concrete, it's going to disappear within about 2 years.
Yeah, there's a certain amount of benching that's been put into place to help with this, and there's a certain amount of judgment that we've been putting into the design to help allow for this as well.
So nothing additional is being done.
There's nothing additional except for the benching that's been put in there to help provide movement of the water and to make it self-cleaning as well.
That doesn't stop cavitation, Peter. Thanks. Okay.
We've got Dave Hindle. Oh, we've handed over to the naughty corner now.
Oh, well, I'll start with a bit naughty. I've been a Hammersmith resident for 40 years, and I've got to congratulate you because I didn't even notice you were there, honestly. Really nice site, neat, very good. But I just want you to confirm something. It's not you that's buggered up Hammersmith Bridge, is it?
It isn't. No.
Right, okay, fair enough. I'm very pleased that with what you've done in that. I've been arguing for 20 odd years that you don't need waterproofing in London clay. Yeah. The one thing I did notice though on your programme, you didn't allow on your programme the time it took you to do the injection sealing at the end, yeah, which I think was a bit of catchy-uppy on the waterproof membrane. Is that right?
The injection was actually done concurrently with the secondary line.
Oh, okay.
So you do the first bit,
Yeah.
you get the shutter in, and then you take it off the critical path.
Yeah.
I think it's fair to say that with every waterproofing system you use, you have to do some injection anyway.
Yeah.
We've tried applying master seal against wet SEL, and that doesn't work very well. So you do have to inject with all methods, in my opinion.
And the designer is happy with this composite lining idea, is he? That it really works.
Well, the design doesn't rely on composite action, so we're relying on the primary lining to take all the long-term loading.
So the primary lining's taking the long-term ground loading, the secondary lining is really taking the surge loading.
Correct.
Okay, happy with that.
We've got Mike McConnell at the front here, Rod.
Yeah.
Mike McConnell, retired Balfour BD. Congratulations, guys. The amount of detail and the actual testing and initiatives in looking at how you can do things better was excellent. I think I'm left with the memory here that you mentioned you're going to transfer that onto the main bore on the western side of things. But from a client's point of view, how are all the good value best practice points being picked up there that Tideway can then try to introduce into the other main contracts so that others are learning from the fine work that you've already done?
Yeah, we very much work as an alliance on Tideway, and any issues, any innovation is just shared openly. You know, we've had issues at Hammersmith and they've already been shared with West Central.
And these other sections.
Yes. Yeah, even throughout the design stages, we held a transformational, it's a health and safety working group, but we also talk about design. You know, one of our key points was we've got an inclined face, and you guys, you should try and adopt that as well if you can. So that is ongoing.
Where's our next question? Andy Sindel, you must be bursting for a question now.
Just talk. Oh yes, it's on. No awkward buttons to press. Great talk, thanks chaps. 1,000,001 questions. Just on the cavitation thing, I was very interested in the vortex. I was involved in Cairo 13 plus years ago, and at the bottom of the drop shafts, we had these whacking great cast iron or SG iron saucers that we cast in. They weighed about 5 tons each, that we put at the bottom to take the abrasion of all the grit and all the other glorious things in the sewage. I wonder what you have at the bottom of the shafts here. Do you have anything like that will take that abrasion?
We do have a lot of bench and out-shaped in discs to help deal with the amount of flow that comes down. So
it's just benching. It's not a material that will really take impact.
The benching material, the concrete that is used, has been specified to high durability requirements, so it should be able to take this.
Yeah. Anyway, my real question was about the SCL shift pattern. We could talk all evening about this. But a quick one on that. You have a 2-shift system, 10 hours only. Do you not get an awful lot of dead time in between? And how do you lose? Do you lose much continuity in output because of that dead time between the shifts?
Yeah.
How does that work?
Initially, we did have dead time, but once we got into the swing of it, the shifts were knocking in 5 rings or 6 rings. And we didn't actually have a gap. We had supervision throughout, so we always had a handover. It worked. It took a few weeks to get into it, but by the end of it, we were getting 15 metres a week, every week.
Donald at the back.
Donald Lamond, hyperbaric tunnel safety. Dust is one of the big health hazards of sprayed concrete work. You obviously did a lot of testing and mixed design for your shotcrete. Did you consider dust as a mixed design parameter? And if not, why not?
Well, rebound was a mixed design parameter. I think we needed a maximum of 15%, and we got 5%. Yeah. But in terms of respirable dust, we didn't do any readings during the trials. I think one thing we should say is that the use of positive pressure-fed RPE on Tideway has gone a lot further than we did on Crossrail. We had airflow helmets on Crossrail, but I remember the maintenance being the lead miner banging his filter on the alley mat as we go down into the tunnel. Now we have proper maintenance regimes in place to look after this equipment. So I think there's been a real step change from from Crossrail to what we've achieved on Tideway.
Well, dust is a natural byproduct, isn't it, of sprayed concrete linings, and throughout the construction of the tunnel, we consistently damped down as much as possible, blew out the dust where possible. We did pretty much as we could do, really, to try and remove dust from the joint location.
Oh, I'm reversing my comment about naughty corner now, Roy.
Well, absolutely. You didn't answer Donald's second question, and there you've danced around it anyway. You've blown away the dust. That's just putting it up into the atmosphere. The whole thing, I must say, it wasn't as obvious on most of your photographs, but in previous presentations here, the one that's been very obvious, on the one on Crossrail especially, excellent photographs, but the mist that was there from the reflection from the dust in the air, and that's respirable dust. You mentioned the helmets, great if you're maintaining them. Did everybody wear them? Did you wear one when you went down?
Every engineer and operative in our SCL restricted area had to wear.
I asked you.
If they were spraying, yes, but I generally go down when they're not spraying.
Yeah, but that's the whole point, that the dust that is still there, maybe not visible, but it's respirable dust.
Yes.
And no precautions were even taken. So, you answered the question there. And that's the whole point. We had a very long discussion in another meeting here earlier about this point with SCL. The whole problem with respirable dust is usually not... you're paying lip service. You give the guy on the nozzle, but the rest of the people you're not. And there you're talking about the dust that was affecting some of the joints. Mm-hmm. And your answer was, we cleaned that by blowing it away. It's not a proper answer. No, well, not a proper solution to the problem. I'm not commenting on your answer.
There's Satiris at the front here. Hello. You've got a microphone.
Can you hear me?
It's been waiting.
Thanks, very nice presentation for Ed and Peter. A question for Ed. You were alluding that perhaps the verification regime of taking course is not very good, isn't it? Is it something that you would like to suggest to avoid in the future?
Are you talking about the workmanship panel?
Yes, or taking course from the actual works.
Well, I think we have to take a certain amount of course from the works to ensure compliance. In this instance, it was quite annoying as we wanted a watertight lining and we were drilling holes in it. But there was no way around that, which is stipulated in the works information.
If there's a way to avoid, you would avoid. That's what I'm trying to suggest here. If there was a way to avoid taking course, you would avoid.
Yes, we would. Yeah.
Certainly. Two other observations. I've heard a lot about design. The gentleman, I think someone was, I'm happy to discuss it in downstairs because it will take some time. The cavitation, I think is a real issue, but as far as I remember, this fills very quickly, isn't the shaft? So the cavitation required is more pronounced where when this hits the bottom, and then very quickly this hits a pool of water. So. Don't know if this
maybe you want to discuss that at the bar, Satiris.
This is another question, but thank you very much for the presentation. This was very good.
One more question, because we do have to press on. Yep, back there. Yeah.
Hi, Alan Scarder from Langeroog. Thanks for a great presentation. How confident would you be to use this waterproofing system in soils, granular soils with higher water pressures like Lambeth Group Sand Channel, Thanet Sands?
It all comes down to being able to get good quality sprayed concrete. So if you can't get good quality sprayed concrete and you can't address the joints properly, then you're going to leave yourself exposed. So it's going to be very difficult to use in, you know, sands or soils.
I think we've got to bash on a little bit now. I mean, it was a fantastic presentation, really good, a hell of a lot of detail in it, and I think we should thank the speakers in our usual way, please. And now I'd like to invite Donald to the stage, who wants to say something else.
Thank you, Mr. Chairman. Good evening, ladies and gentlemen. Right, tonight I want to talk about British Standard 6164, Safety in Tunnelling. I could tell you that the revision of BS 6164 has been completed and the document will be published sometime late in October. However, tonight I'm here for a different reason. I want to recognise the contribution which one of the members of the 6164 committee has made over the past 35 years or so. He's been heavily involved in 4 revisions of the standard. When I send out text for comment, he's always amongst the first to respond. Sometimes he responds before I even ask for comment. In the latest revision, as in the others, he has worked on and been responsible for many of the changes in the sections to deal with plant and equipment. This is the British Standard Institution Distinguished Service Certificate, and I'm very pleased to ask Peter Remnant to come up and receive the certificate for all the work he's done on BS 6164 over 3.5 decades.
Thank you. Well done, Peter. So from the young Turks to the elder statesmen, eh? So could we have the chair slides now, please? We've been promising an evening out of London for some time, and here it is. Tuesday, the 15th of October 2019, 5:30 in Newcastle. Subject will be building damage and Bond Street Station, building damage assessment. BTS will be providing buffet and drinks afterwards. And for those of you who want to, Rod Young will be providing a guided tour of the clubs of Newcastle after that. It's up to you which part of the menu you want to select, but please, if you're in that area, please go up and enjoy the night. Next, please. So, as you know, we're coming up to our 50th anniversary, and we're putting a call out for sponsorship. There was an email sent out 2 days ago, I believe, for sponsorship for corporate members and individual members. We've already had a number of positive responses. I think we've had 3 corporate members coming forward already offering sponsorship. And more impressively, a number of individual members coming forward and offering sponsorship as well. So if you've got any questions on sponsorship, see Anita Wu in the bar. Next, please. Call for content in the book. We have today put aside a budget for the publisher. We've got a lot of stories, we've got a lot of raw material. But looking at you all in here tonight, there's a whole load more to harvest. So if you have a story to tell, amusing or otherwise, see John Corcoran or Ken Spivey at the bar. Next, please. We've opened up bookings for our health and safety course to be run at the end of November. The prices opened up, I think, on Monday. Prices are £155 for members and £190 for non-members. I think, Ed, you spend more than £155 on your shoes, don't you?
It's true, yeah.
This is a two-day course for £155. And it is filling up fast. So if you want to save on the shoes and go on the course, this is it. Next, please. Now, Anita has given me a lot of words to read out here, so if you'll bear with me, I'm going to read them out. She says, however, would you mind reading a longer bit, please? The BTS are now incorporating data from the Transforming Tunnelling Safety Group, TTSG, onto our website. TTSG aim to drive a step change in tunnelling safety, health and welfare. One route identified as contributing to this is that we must, as an industry, improve the way we learn from our experience. It's very much touching on the questions asked tonight. Therefore, we have opened a portal for the sharing of good practice and lessons learnt. On the TTS webpage, you can find safety videos, health, safety and welfare lessons learnt, good practice guides, good practice proposals. TTSG would like more contents on the website with your contributions. To date, we've had contributions from Vinci Construction, Balfour Beatty, Morgan Sindall and Tideway. So please, more contributions if you have them. If you have any information that you want to share, please contact Nick Butler, and Nick Butler's email is there, quite simple to remember, nickbutler@mopmac.com. Okay, next, please. So, moving on to our calendar looking forward. Our next meeting is on the 17th of October, and it's going to be all about drift-filled hollows, pingos, I think, more on London clay. Next, please. That's a geological section, I think, of what... Is that a pingo, John, is it? Yeah, there's a pingo. I'm not sure what the other picture is, but you put it there for some reason or another. Moving on from that, please. On the 14th of November, you'll all remember that this is the anniversary of the Channel Tunnel opening. We've invited Bruno Comp of Bouygues across to give the Harding Memorial Lecture. And Bouygues have recently certainly been market leaders in terms of innovation in TBM tunnelling. This is another good reason to come on Thursday, the 14th of November. And I think Bruno's, next please. Bruno's put in a couple of pictures of the innovation at Tin Mon using a TBM for cross-passage construction. Next, please. Right. Firstly, I would like to thank Mike McConnell for his sterling attempts at bringing the Institution of Civil Engineers to heel on refusing to serve us with sausage and chips and pasty and chips. Mike taking up his shillelagh and certainly gave the responsible director a battering that he will remember for some time. The good news is that the Institution of Civil Engineers are bringing back sausage and chips and pasty and chips, but not tonight. The bad news is that they're putting the price up to £4.73 for either. The good news is that they'll be providing, well, maybe not, they'll be providing baked beans as well as the sausage and chips. So, the Tunnelling Society have today decided to take the risk on numbers. The ICE were concerned about the numbers taking up the meal. We have offered to take the risk on numbers. So please do call in next month for your sausage and chips. And we do have a plan to look at sponsorship of the sausage and chips as well as the bar. So that price might come down. Right, next please. Right, I think it's fantastic to see so many of you here tonight. Ed, in his part of the presentation, a testament to the highly skilled and experienced workforce and supervision involved in the construction of tunnelling. And it's so good to see so many supervisors here tonight. We engineers find 101 ways of not doing something, leaving the foreman to find the one way of doing it. So please, those of you who are supervising, please come along in future. You are the backbone of our industry, and more than welcome on a Thursday evening or any other activity of the Tunnelling Society. Now, the good news for all of you is that the bar is sponsored tonight by CPI and Morgan Sindall Engineering Solutions. So that was a spontaneous applause for the sponsors. And without further ado, the bar is open. Thank you.